Title of this talk is Approximation of Sobolev function. Riddhi, Mishra.
Yeah. So today we are going to see how to approximate any Sobolev function by the title Approximation by Smooth Function. So the first question, Sobolev function has smooth approximation. Does a Sobolev function has a smooth approximation? And the answer is true. We can make given Sobolev function with a smooth function. So before to study the topic, I want to introduce some smooth function example, which we have seen in complex analysis. That is the example where the function is not complex analytic, but it is a smooth. So we consider on Rn by P given as exponential function times some constant whenever this is a unit ball and 0 outside of this unit ball. Then I define this phi by assuming C such that this integral of phi over Rn, this is 1. This we call, phi is called here, is called as a standard modifier. Or Frederick modifier. So you can check this is a smooth function by calculating all the derivative, and you can also check this is not an analytic function because every derivative at the point 0 when you say function is not identically 0. Okay. So with the help of the Frederick modifier, I will try to define the support. The support is in a unit ball, and now I will try to define different modifier where the support is in some ball with radius epsilon. So I set epsilon positive. I define phi epsilon at x 1 over epsilon to the power n, and I divide the support by epsilon. So function, the standard modifier has support in unit balls. So here support is the phi has support in a unit ball, means now the support of phi epsilon is in B0 epsilon. So most of the time you want to support very small. So this epsilon will play an important role when I will define the convolution. Okay, and we will see the phi, this phi epsilon when I integrate over Rn, this also goes to 1. So let's see how we will do it. And now we have I will use the change of variable. Set x by epsilon is equal to z, then we have dx is equal to epsilon to the power n dz. This is the Jacobian of this transformation. So we have r in phi z dz. And we know that for a standard modifier, we have the integral 1. So this is this phi epsilon for any epsilon positive. This integral of phi epsilon over n is 1. And support of phi epsilon is in a ball with radius epsilon. Okay. Now the second is, I will try to define some notation. So the first notation I am going to give is for any epsilon, I define omega epsilon. So all those, this set is a set that contains all those points in omega whose distance from the boundary is at least epsilon, means greater than epsilon. So the picture is like, this is my omega. So I go little bit far from the boundary, and this distance is epsilon, and I will make a set. This is not so precise, but this is my omega epsilon. Why I am doing this? Because I want to define convolution. So let's first define convolution. So convolution can be defined for a locally integrable function. So it's a very general concept. So let f be any locally integrable function, which is defined on omega. Then we define the convolution as f star phi epsilon. So this star is a notion of convolution, and I define for a function, a convolution is f star phi epsilon, and this is defined as at a point x as f x minus y phi epsilon y dy over omega. Here this f epsilon is a convolution of f at a point x in omega. So basically, convolution is also a function on omega, and it is a real valued function. So here we will see by change of variable that here the function should be defined only in omega epsilon. So why I'm saying this? Because f epsilon phi, convolution phi epsilon x at point x is, by definition we have this x minus y phi epsilon y dy. Now phi epsilon in b0 epsilon. I can write b0 epsilon because the integral will give 0 outside the support. Epsilon y x. This was my omega, and this is my omega epsilon. And my y is in b0 epsilon. So if I am here on the boundary of omega epsilon, and I will take y in this range b0 epsilon, then this value, the function value at this point should make sense. So that's why we are a little bit far away from the boundary, so that when I make this ball with epsilon radius, this ball should contain inside the omega. So that's why here this f convolve phi epsilon is defined on omega epsilon. Instead, integral is over omega, but it is defined on omega epsilon, not on the omega. Because then the problem will occur. Suppose you are taking point here and you make a ball with radius epsilon. Then here the function is not defined. So we have to take this account at some point. That's why we are not going out. We are considering this omega epsilon. So some remark about this. The first one is, if my omega is Rn, then we don't have any problem. Have this problem. Because then you are not worried about whether your ball can go outside the domain, because now your domain is whole space. And the second, by change of variable. By change of variable, z is equal to x minus y. We have f x minus y phi epsilon y is same as f z phi x minus z dz. You can compute this because then the dz will be dy and you just transferring from this variable to z variable. Okay. The third one is for every epsilon positive and for every x in omega epsilon, we can calculate epsilon x. So what, not f epsilon, we can calculate this f convolve phi epsilon fx. This absolute value, by the definition, we have f x minus y phi epsilon y dy over omega. And now you know that this phi epsilon is a standard modifier, so it's a smooth function, so you can take the L infinity norm outside. So you can take this outside by L infinity norm, and then you have bx epsilon phi y dy. By using change of variable, you can transfer this unit ball to by translation, you can transfer the b0 epsilon ball with b x epsilon, means you are transferring the center from origin to center x. And now
Hello.
yes,
How you did the last line? Less than equal to then
this one, okay. So let's do complete. So this you can write Fy phi epsilon. Okay, let me do more clearly now also. No step. So you can write this. This has support in B0 epsilon. So you can write this integral at B0 epsilon fxy minus y dy. And now you can transfer this with center x. So you change variable by z. Then you can write this as b centered at x with epsilon fy epsilon x minus y. So here y is dummy variable. So I replaced y by z here, but it's still same. And now here phi you can go inside. This is always bounded above by L infinity norm. So this is because L infinity norm is the supremum, essential supremum. Is it fine?
Taking x minus y equal to z.
Yeah, okay. So you can replace
Yeah.
here y by z because it's a dummy variable. Then also doesn't, because z you can write y, so it doesn't makes any difference.
Yeah, now this one.
Yeah. Okay. Now there we have properties of this modifier. So the first one is for f convol phi epsilon, you can check that this is a smooth function. And more precisely, for any derivative, you can transfer the derivative to the modifier. So this is phi epsilon at any point x. So this can be done by computation. You can calculate the derivative of this this modifier, and then you will get that okay, the derivative is also a convolution of f with the derivative of phi epsilon. And the second one is this convolution converge to function f almost everywhere in omega epsilon. So this convergence is pointwise in your domain omega epsilon as epsilon goes to 0. Third one is if your function f is a continuous on omega, then you can find, then this convolution, this convolution converges uniformly to f in omega prime, where omega prime is compactly contained in omega. This means that if your function is continuous over omega, then the convolution converges locally, converge uniformly to a function locally in omega. And this is very strong, a strong property, because from a continuous function, you are approximating that function with a uniform convergence of this smooth function. So this function is very good in some sense that they are very smooth, and you are approximating just a continuous function locally, in fact locally uniformly with a smooth function. So you can expect a lot of properties being transferred with this uniform convergence of this smooth function. Okay, and the fourth one is, if my function f is locally LP for P in this range, then this convolution converges to F in LP, where omega is compactly contained in omega prime is compactly contained in omega. So what this shows that if your function is locally integrable, which is LP locally integrable, then also you can approximate your function with this convolution. But this approximation is not global. This you can approximate locally. And you can see here I'm not using equal to infinity because this cannot hold. This means this 4 cannot hold when P is equal to infinity. Why? Because this L infinity function is not a good class. L infinity function contains a lot of discontinuous function. And if you are converging locally in L infinity sense, then you are actually uniform convergence. And these are continuous function, and uniform convergence of a continuous function transfer continuity to the limit. And here my L infinity at omega contains a lot of discontinuous functions. So if you choose any discontinuous function here, you cannot approximate that discontinuous function with a uniform convergence of a continuous function, because the limit cannot be discontinuous under the uniform convergence of a continuous function. Is this make sense? Am I audible?
Yeah, yes, please go ahead.
Yes.
Okay. Okay, so now the next topic is local approximation. Local approximation in Sobolev space. So when I introduced the Sobolev space definition, I forgot to mention that the Sobolev space is actually a Banach space. So that means that it is a complete space. So we can talk about the approximation, because then we are sure that, okay, if the limit converges, then the limit should be inside the Sobolev space because of the completeness. So now we will show that convolution approximation converges locally in Sobolev space. So the first thing to notice here that I am not demanding any regularity on the domain. So for me, omega is just the subset of Rn which is open. I am not assuming any kind of regularity on the boundary. So we are sacrificing here, we are not assuming any boundary condition on the domain. So that's why we are getting locally convergence. Locally convergence in the Sobolev space. And if we have a boundary regularity on the domain, then we can get a global convergence. So we will discuss the next topic where we have global approximation. So what the theorem tells us that for any a function in WKP, where P is 1 to infinity, I am disregarding the case when we have L infinity norm because of this discontinuous behavior. Then the first claim that the weak derivative of U convolution phi epsilon at point X is same as the weak derivative U convolution with phi epsilon at the point X in omega. And the second one that this U convolve phi epsilon, this converges to U in WKP setting where omega prime is locally compactly contained in omega. So for any open set, you choose any open set in domain in Rn, and you take any function which is W1, WKP in this domain, then you can approximate your function locally. Let's say this is your point, and you can approximate your function locally in this neighborhood with a smooth function. So this is what the local approximation of your Sobolev function with smooth functions. And how to prove it? Here, to prove the first statement, we will use the integration by part 2 times. And this is just taking the norm because we know that this is, we can transfer the convolution to the first function because we know that the function has weak derivative. But this is always true that we can transfer this with the second one because we know that this derivative exists. This is always true irrespective your function is differentiable or not differentiable. But this equality is something new because you are transferring this derivative to your first component, and this makes happen because U has weak derivative, because U belongs to Sobolev space and it has weak derivative by definition. So you can transfer the derivative to your first, Okay, so the proof, how the proof goes. So fix a point X. So what is the goal? So let's write the goal first. Goal is we have to calculate this U convolve phi epsilon at
I
X.
think they were already in some lips.
when
Yeah,
x
yeah,
is
but because they didn't
yes,
discuss that. These are very simple. Actually, compared to our function, that's okay. Because primary reading is there. If
can you
Okay.
please unmute?
like
Yeah.
Just wait a minute.
Now fix a point x in omega epsilon. Then what is d u convolve phi epsilon at this point x? By definition, this is this we know. This is, you can prove this. This is u convolve d alpha phi epsilon. So this is a property of modifier where we have seen this, that these modifiers are smooth. And now this is over omega. I will specify the x because I am integrating with respect to y. So phi epsilon x minus y uy dy. And now I want to give the because here the integration is with respect to y, so I want to give the weak derivative with respect to y so that I can use the integration by part. I cannot use integration by part now because weak derivative here is in term of x. So to use the weak derivative notion or to use the integration by part, I need that here the derivative should be in the term of y. So what I will do, first observe this. So this I can write by definition, this is x by y by epsilon. And now I can write this phi y minus x. I change the order. So minus will come here. And now I will change this dummy variables. So this I can write this yj phi x minus y. So okay. So here the derivative was with respect to x. And now when I change the derivative with respect to y, then the minus sign appear. So what I will do here, I will write this as, because this is a multi-index, and how many times you will do this minus times keep in iteration. So this minus to the mod alpha will come, and then you had transferred the x with respect to y. Minus dy. And now you can use integration by part because now your derivative is also with respect to y and you are integrating with respect to y. So by integration by part from here, you will get plus 1. This is first one. By integration by part, you get 1 extra. And now you have transferred, where is u? You have transferred this derivative to u because now u has a weak derivative. So you have transferred uy dy. Omega. And this is minus 1 to the power 2 alpha, which means that 1. So these terms disappear. And this is same as d alpha of u convolve phi epsilon at x. So this means that we have transferred the derivative to the first component by using integration by part. Is this clear?
Riddhi,
Yeah.
I have one doubt. Here you are using some dummy variable that in last line. I think here.
At this point?
No, right side. Can you
Here?
see my? You are saying that here that changing x by y. How you are doing here?
You can just you can change it because you can take xj because you are transferring y. Sorry, here xj is here and x is here. Now you can do by okay. So first thing, let's do by one when when you have x and you have y. So if my function is, let's say, x and y, so when you derivate with respect to x, this means that you have to derivate with respect to x, and then also there is one more variable y also. Is something wrong?
My question is that in first you are taking derivative with respect to x. After that you are changing that y. How this is something I don't know.
Because x is also x and y both are variable. No. And you are changing the variable.
No, that is nothing.
Can you speak again?
Saying that here how you are changing the x to y.
Why can't we do that? Because they are dummy variables. No?
Okay, you proceed. I will see.
Okay, give me 1 minute to find a concrete solution. I have to send.
Okay, Riddhi, you can proceed. We'll talk
Okay.
later about this.
Okay. And the second one is I have to show that U convol phi epsilon converts to U in WKP omega prime, where omega prime is compactly contained in omega. So let omega prime is compactly contained in omega, and I want to find the convergence of this sequence on this set. So what I will do, I will choose epsilon positive such that this omega prime is outside contained in omega epsilon. So okay, so this was my omega. And I know my compactly contained set omega prime is here. And now I will choose some epsilon so that we are from the boundary, because I want to make here a ball. So I want to make sure for this point, if I make a ball, it should not go outside my domain omega. So I will cover this with omega epsilon so that this, if I made the epsilon radius ball, it will be inside this omega epsilon. So, and now by 1 we have d alpha u convol phi at point x. This is d alpha u convol. And this we have for x in omega prime. So we are looking at here, not in whole set. And I want to approximate my convolution approximation in this open ball or open compactly contained set. So this is true for, and we know that if we have f is a locally integrable function, then f convolve phi epsilon LP. This converts to f in LP locally. So this we have from the property of modifier. So this means when it's very rapidly, then this convolution comes to the alpha u. That means d u convolve epsilon converts to d alpha u in LP omega as epsilon goes to 0. So we have this ball or this compactly contained set, or compactly contained set is the ball, small ball. So consequently, U convolve the phi epsilon minus U. So definition we U convolve, sorry, E epsilon minus D alpha U. This is just a definition of WKP norm. And here this alpha is less than equal to K. And we know that epsilon, U epsilon D alpha converts to the alpha u by this previous. So this means that this is less than equal some epsilon or some delta as epsilon goes to 0. Prove what epsilon to the form. So now we have the local approximation of my Sobolev space, and now we are going to see the global approximation of Sobolev in Sobolev. So global approximation. In Sobolev space. So this was proved by Meyer's setting. The statement is if U is a function in the Sobolev space WKP, that they are also discontinuous function, then there exist functions UI which are smooth, but this smoothness is not arbitrary. We are taking this intersection also. Such this UI U in WKP. So here we are trying to approximate globally, but we cannot do with only a smooth function. We have to take a smoothness intersection WKP. So to find a global approximation, we are setting the very large set. We are not in the very. We have not enough choice of this function. The restriction is now the smoothness and in the Sobolev class also. So you cannot take just the US function and you can find the smooth approximation of your function in the whole space. The smooth approximation is only in the local sense. But if you are talking about global approximation, then you have to take the intersection with the Sobolev class. Otherwise, it's not true. And the proof is highly based on the partition of unity. I will explain the sketch, not the whole proof. Sketch of the proof. So this is my domain omega. What you will do, you make partition. Of the set. So you will define this omega I as all those points in omega such that distance from the point to the boundary of omega is greater equal 1. And you take this with B0 I. So omega I is a cover of your omega. So you can check that omega I union. This is omega. So you have a cover in omega. And now what you will do, you will take you will construct some function eta I. So, such that eta I is 1 in every consecutive omega. I have to write explicitly, so so you have omega is you partition omega with omega I. This is slow. Yeah. Okay. Now you took this omega I plus 2 minus omega I minus 1. So you make two patches. So suppose this is 1 and line. So this region is sum I plus 2 minus omega I minus 1. So you want to define a smooth function eta I tilde. This is compactly supported in I minus 1. This means that here is 1 and here the function goes to 0. So your function is 1 here and this goes to 0. Like eta I tilde is, and eta I tilde is 1 in omega I plus 1 minus omega I. Okay, so you can find this kind of cutoff function by using partition of unity. And now you define eta I. It's very slow. You define eta I is eta I tilde over to make it a partition or J. So this is my partition of unity subordinated to this cover of my domain omega. And with this partition of unity, you multiply your function u to make the truncation. So this will truncate your function. So you can check that if u is in Sobolev and you multiply that Sobolev function with some CC infinity function, then the multiplication, this whole multiplication is so suppose eta IU is same as your eta tilde. Minus 1. So this is a property of modifier or property of weak derivative. So now you have for your function, you have approximation on each this patches. So you and now what you will do, you will cover this patches. This is patch modifier to make it smooth. So so these patches will look like in this patch you have this. The rest you have 0 for 2 annuli. And similarly here you 5 and 3, then in between this also, this patches is like this. In the conjugative also the patch like this. So next thing we want to make the continuous modification. So when you will multiply with this function, this will give the smoothness to each together with this function. So what I am trying to say, now I will take the convolution phi epsilon I eta I of u. So here I fixed this is, and for this positive I will try to convolve this function so that this is smooth in whole omega. It is smooth in whole omega. So this is a smooth function, and you can check that support of this function for each I. This is inside. So this is omega plus 2 minus omega I minus 1. So you have approximation in each passage, and this so this means that you can combine by partition of unity so that this is a smooth function over all omega. And you can find that this phi epsilon I convolution eta u minus eta I of u, this WKP is less than fixed constant. Yeah, so you can approximate your W function with this smooth approximation. So this we wanted to prove. Now we define V is equal to, because I want a whole approximation, so I will convolve this I from 1 to infinity. And then you have to check that V and U WKP norm over omega. I of U. This is a partition of unity, so the summation is 1. Actually, I am writing only U here. And this is same as my keyboard is very slow. Yeah. Summation phi ln I convolve eta I u minus u eta I u. And we know that less than equal to, so this is less than equal to epsilon. Yes, you take your I is from 1 to infinity. This proves that U is approximate with this function V. And you actually here your eta IU is WK. So that's why this modification is a smooth intersection WKP. It's not only smooth, it has extra property because this is in Sobolev. Yeah, I will end here.